Today we are going to talk about mirrors. Let's start off by reviewing the law of reflection. When we have light that enters a reflective barrier or boundary, that light is going to bounce off so that it stays in the same medium that it originated from. Our incident ray is how we identify the light that comes into our reflective boundary or surface. The light that bounces off will be called the reflected ray. And we can measure the angle that the light comes in, and we can measure the angle that the light goes out. And the law of reflection says that these two angle values will be the same. If you look at the illustration, you can see that our angles are not going to be measured from the reflective barrier or surface, but instead those angles are going to be measured from something that we call the normal line. So the normal line is an imaginary line that is perpendicular to that boundary or surface. So the blue dotted line in this illustration represents our normal line. The angle that we measure for our incident angle is from that normal line, and the angle that we measure, our reflected angle, is also from that normal line. So this is the behavior of reflected light whenever we have reflection off of a very smooth barrier or surface, and this is known as specular reflection. The mirror is going to cause the light to bounce off, and that reflected light is then going to make it to our eyes, and our eyes are going to interpret an image from the light that is received. So we have two categories. We have virtual images and we have real images. Let's actually start off by talking about real images. This occurs whenever the beams of light bounce off the mirror so that they physically meet up somewhere. Real images can be projected onto some sort of surface. So anytime we are discussing the behavior of light, if the beams of light bounce off in such a way so that they physically meet up, we are going to identify that as a real image. A virtual image, on the other hand, is an image that is created not because the beams of light join up to make an actual picture for us, but the light that reaches our eye is interpreted, and the brain takes that information, and although the light doesn't physically meet up to create the picture, our brain fills in the missing information and forms a picture for us anyway. As we begin to look at some illustrations of the reflected light, this will probably make more sense, hopefully. All right. Plane mirrors are regular flat mirrors. Most people, when you go into the bathroom, let's say you're standing at the sink washing your hands, you can see yourself in the mirror. That is typically a plain flat mirror. So the image that we are going to get off of plain flat mirrors are going to be the same all the time. These are always virtual images. The object in real life is the same distance from the mirror that the image appears to be. And the object in real life is the same height that the image that we see in the mirror appears to be. So let's look at the illustration here on the left. When we are talking about virtual images, that's what we see every time we look in a plain flat mirror. Now, the light that comes off of the top of this chess piece goes into the mirror, and it's going to bounce off. So here is my incident ray, and then here is my reflected ray. So your brain receives a signal from this beam of light. Your brain does not know that this beam right here even exists. So we will never interpret that beam whenever we're trying to understand what kind of image is created. Instead, we are going to interpret only the beam that reaches our eye. Now, light travels in a straight line path, so the light that comes to your eyeball here, your brain assumes is traveling along this line. So your brain does not understand that the other side of the mirror contains a wall. Your brain does not understand that the light came from a mirror. Instead, your brain assumes that the light came from back here. So this is where the image appears to be because your brain is taking learned information which says that light travels in a straight path. So the light came to me from this direction. That's because that's where the light originated from. Now, in the illustration, you may have noticed that they do not have a solid line on the right-hand side of the mirror. That is because solid lines will be used to illustrate the actual physical path of light. Guys, the other side of the mirror is the wall. The light is not traveling through the wall in this situation. Okay, so the way that we're going to illustrate this is instead of having a solid line, which would indicate real paths for the light, we are going to use dotted lines, which are there to tell us that this is what our brain is being tricked into thinking is the path of light, but this is not where the light actually physically travels. And so as we look at the various light that comes off of our chest piece in this illustration, we can see that all of these beams of light, according to my eye, came from this direction. So it traces everything back to the right side of the mirror, or in this case, behind the mirror. So every time you look in a plain flat mirror, the image that you see is virtual because the light appears to come from the other side. The pencil that you see in the middle picture is showing you that the height of the pencil is the same in real life compared to the reflected image from the mirror. You can also see that the distance that the mirror is in real life is the same distance that the image appears to be. And so the easiest way to explain this or give you some sort of better, clearer understanding of this, again, imagine that you are in the bathroom, you're standing at the sink washing your hands. You didn't get taller because you're looking in the mirror, right? You didn't get any shorter. However far you are standing from the mirror is how far your image is. So if in real life you are standing at the edge of the counter, your image is also located at the edge of the counter, okay? What if instead of a plain flat mirror, we have a curved mirror? Now, because of the curved surface, that is going to alter how the light reflects off of the mirror. So, curved objects, if we take that curve and we just continue it, well, we end up with a circle, right? So it says here that the radius of curvature is one of the measurable properties of our curved mirrors. So if we allowed that curve to continue and make a circle, here's the center of my circle, there is my radius r. We are actually going to be focusing on a distance that is half of this measurement, and so that is going to be called the focus or the focal point. And so we're going to represent that with the letter F. Now, I apologize, some of the font did not transfer over properly whenever I uploaded this to my iPad, so I'll make some corrections as we go for the notations. But the F is going to stand for the focus, the focal point. When we do our measurements on our ray diagrams in the next lesson, then this will sometimes be referred to as the focal length. The DO, this should be a lowercase d for distance and then a subscript of O for object. This is how far away our object, our real life object, is going to be placed from the mirror. DI is going to stand for the distance to the image. This is also going to be measured from the mirror. We're going to use a lowercase h for height and a subscript of I for image. So as I was talking about the pencil, how tall it was in real life compared to the reflection, HI is going to be the height of the image. HO is going to be the height of the object. M is going to be a capital M for us, and this will be the magnification. So in other words, based off of the value for M, we will be able to interpret whether the image has been enlarged or reduced. So is the reflected image bigger than the real life object, or is it smaller than the real life object? In some situations it would be the same, so our M value on a plain flat mirror would be 1 because it's the same as the original. But for our curved mirrors, it is not going to be the same. It'll be either a decimal because it is smaller than the real life object, or it's going to be some number larger than 1 because the image is greater than the real life object. There's some more detailed information in these boxes over here on the right, and we will revisit those later in the lesson when we look at our formulas. The first type of curved mirror that we're going to discuss is a concave mirror. Now, in this chapter, you need to be familiar with the words concave and convex, converging and diverging. We're starting off the chapter discussing mirrors, and then later we're going to talk about lenses. The words concave and convex are used to describe the shape or the curvature. So in general, the word concave, in order for us to interpret what the shape should look like for a concave mirror, we need to understand our point of reference. So for a mirror, let's say that I am standing in front of a curved mirror. If, from my perspective, it seems as though my person could be walking into the cave of my curved mirror, then we are going to call that concave. Okay, this is where the curvature moves inward or away from the object. If we have it flipped around so that instead of curving in away from you, it comes out towards you, then that is called convex. And again, we are simply interpreting the shape of the curvature with the words concave and convex. Now, when the light reflects off, you can see from this image in the top right-hand corner, here we are showing you multiple beams of light. So the top beam is going to strike the mirror at the top of the curvature. This middle beam hits smack dab in the middle of that curve. This bottom beam at the bottom edge of the curvature. So this is showing you at the different locations how the light is going to reflect off. And what we see is that all these beams of light end up bouncing off so that they join up together. So this coming together of the light is referred to as converging light rays. So whenever you hear the word or read the word converging, so converges, converging, this means that the light beams come together. Now for mirrors, a concave mirror causes the light to come together, and you are going to need to know your mirror and how it affects the light. So you will need to know when the mirror creates converging light rays, because we're going to use that information when we plug numbers into our formula. You can see on the slide that it says that we have 3 different options for what our image will look like. If you look at the picture of the boy and the girl here on the bottom right of the slide, you see that the boy is standing farther away from the mirror and his image is upside down. You see that the girl is standing right up on the mirror and her image is right side up. You may also be able to tell that her image is larger than the real life size of the girl. With the boy, it's not quite so clear, but usually whenever we are that far away from the mirror, our image ends up being smaller than the actual size of the object. So you can tell that the 2 kids are standing at 2 different distances from the mirror, and we get 2 different results for their images. And so that's what we're telling you over here on the bullets of this slide. If we stand outside the focal point, so remember, the focus is just this distance, some distance from the curvature of the circle. So if here's my mirror, then my focus would be some distance away from that mirror. Okay, now every mirror has its own focal length, and it is dependent upon the curvature of each individual mirror. So whatever the focus is for our mirror, if our object is standing farther away than that position, then we will get an image that is smaller, inverted, and real. This boy's image is a real image. Now, that doesn't mean probably what you instinctively think. You're thinking, how is it real? It turned him upside down. Remember, our definition of the word real just simply means that the light physically came together at some point. Look at the picture over here once again in the top right hand corner. These light rays are being bent so that they are trying to come together. So if we put our object far enough away from the mirror that it is past that focal point, then indeed the light will bounce off so that it does join up. So that would make a real image. If we were to place our object on the focal point, we would actually get no image, which sounds kind of trippy, but it's pretty cool. And then if we place our object inside of the focus, and what we mean by inside is that it is closer to the mirror than the focus. So if we were to have our curved mirror, and then let's say that our focal point was here, if we were to place our object somewhere between the focus and the mirror, inside, closer to the mirror than the focus, that's where we get the last option, which is for us to have an image that is upright and that is virtual, and usually our image is also larger than the real life object. Here are some examples of some ray diagrams. We're actually going to learn this in the next lesson, but I wanted to go ahead and show you what we will be using in order to create our image. And this is how we know whether it is real or virtual, inverted or upright. So we can see from the picture here of the boy and the girl that it gets two different images, and I can tell you, and for some of you just being told those facts, and you're going to learn those and you're going to remember what's what, that may be sufficient for some, but really I want you to understand how you're supposed to determine that. Where does it come from? And so that's what we're going to learn in the next lesson when we learn how to create these drawings, okay? What I want to point out to you right now is all of these illustrations or ray diagrams are showing us a situation where our object is located inside of the focus. So super close to the mirror. You see they all create virtual images that are upright and end up being larger than the real life object. These examples show our object is located farther away from the mirror than the focus. So outside of the focus is what we said earlier. And so both of these examples give us a real image, it is inverted, and it is smaller. Now, if you are looking at this and you're not quite sure how I made all of those interpretations, no worries. Next lesson, I'll make it real nice and clear. The opposite of concave is convex. So if concave is a situation where the curvature caves in away from our perspective, then the convex mirrors are going to bow out towards you. So this is where the curvature comes out at you. So if I am here and I'm looking at the mirror, a convex mirror is going to bubble out towards me. Okay, again, it's from the viewer's perspective. So in this type of curved mirror, our light rays are going to diverge. So we understood, or we explained in the last type of mirror, that converge meant to come together. So diverge would be the opposite of that. And this is going to cause the light to spread out. All right, so diverge means to spread out or to separate. When we have a convex mirror, the light is going to bounce off in such a way that all of my beams of light are going to move away from each other. And so we will call that diverging. These types of mirrors are always going to create virtual images. They will be smaller than the actual object, and they are going to be upright. In this situation, we are going to need to understand that these beams of light are never going to physically meet up. If you look at the drawing that I sketched in the top left-hand corner, all of these lines are showing that the light is spreading out and moving away from each other, so they're not going to physically intersect. So any image that is created from these light rays are going to be because our brain made some assumptions and filled in some gaps and created an intersection point for us that it then used to come up with the picture. Okay, the example here is the big mirror that we sometimes see in the hallways at the stairwell of the school, so that you can see around the corner, or maybe you see these in the gas station or at the pharmacy, so the clerks can see around the corners or down the different aisles. And then we also have the example here of the side view mirrors in our car. It says warning or caution, objects are closer than they appear. Our brains are amazing, and our brains interpret so much information at such a quick speed. It is really kind of crazy when you stop and think about how much is done without us even realizing it. So one of the things that our brain does is it remembers previous experiences. So when we receive an object like a car, a real life car that we drive in, and that car appears to be small, our brain has learned that small cars, small real life cars, must just really be far away. So our brains see the pictures of the car in our side view mirror, and because they are smaller than what they should be, our brain just automatically assumes that those cars are far away from us. So they put these warning signs on the side view mirrors to remind us, hey, that car is really closer. Be careful before you switch lanes, okay? Because this is a convex mirror that's going to create a virtual image that is smaller than the real life object. Here are some examples of what those ray diagrams are going to look like when we get into this tomorrow. And what I want to point out here is for all of these examples, our object is placed at various distances from the mirror, and in every situation, they all end up with virtual images. And that's all we really need to understand for now. And guys, I apologize if you can hear all that noise. I have my puppy. I'm trying so hard to ignore him, but I'm sure y'all can hear him, so I'm so sorry. Okay, moving on. Here are the formulas that you guys are going to be using in this chapter for our mirrors. Now, this equation over here on the left, let's talk about what this means. This is a formula that would allow us to use the distance to the image, again measured from the mirror, the distance to the object measured from the mirror, or the distance to the focus measured from the mirror. So we could solve for any of these three things depending on what information we are given. For the practice work that goes with these formulas, you're just going to read some word problems to start off with, and you're going to just learn how to identify your variables and put them in the proper places in the formula. Now, there is some detailed information that I skipped on a previous slide, and we're going to talk about the positive and negatives and when we're supposed to have what in just a moment. But in general, I just kind of want you to get some experience with plugging the numbers into the equations. When we do our ray diagrams in the next lesson, I'm going to show you how the image corresponds to the formula and hopefully clear up any gaps that you may have in comprehending what this equation means or how we're supposed to interpret our information from just the calculated values. Once again, DO should be a lowercase d for distance, and so should DI. So this equation, what I want to point out and warn you about is the fact that everything is written as 1 over. So let's just assume that we have a word problem that tells us that we have an object that is placed 3 centimeters from the mirror. And maybe they go ahead and tell us that this mirror is going to cause an image to be created that is located 5 centimeters from the mirror. So here's my DI and my DO. If I ask you to calculate the focal length, or how far from the mirror is the focal point, then this is the formula that we would use. I would like to point out to you that we have everything written as 1 over. So I'm going to say 1 over f is equal to 1 over my distance to the image plus 1 over the distance to the object. When you see this, you may be very tempted to say, oh, well, I can just say 1 over 8. No, you cannot. That is not the same calculation. You have to do 1 divided by 5, 1 divided by 3, and then add those two things together. If you have your calculator, feel free to go ahead and put this problem in. 1 divided by 5 plus 1 divided by 3. Make sure you put parentheses with that. And then go ahead and just say, well, what if I wanted to say 1 over 8? Put that in your calculator, guys. You're not going to get the same answer. It's not the same calculation, okay? So be careful of that when you do your math work. Now, once we get our answer here, so I'm going to go with my famous 1, 2, 3, 4, 5 made up value, okay? So once we get that answer, that is equal to 1 over f. If you were in math class, you would not leave your answer expressed as 1 over x. You would need to do the necessary algebra to make that x equals. So we have to do the same thing with our focus. I would multiply both sides by f, so f cancels out on the left. So then that means that I'm going to have 1 equals, and then this is being multiplied together, so that I would turn around and divide by whatever that value was, so that I get f equals, and then there's my fraction. If you didn't catch it on your own, let me point out to you, all I did was flip my values. I had 1 over f equals 0.1234, and then if you look at what it simplified to, it simplified to f equals 1 over 0.1234. Okay, so the sooner that we can recognize that we're just flipping that, then the quicker we can be more efficient with our calculations. So when we are doing our math work, we're going to simply take whatever our previous answer was when we did our fraction addition, and we're just going to invert it. Now, when we're working on our calculator, what function means 1 over something? Well, that would be the inverse button. Now, hopefully, you have used your calculator enough that you already know x to the negative 1 would be our inverse button. Hopefully, you already know that any exponent that is negative belongs in the denominator. So some of you may not have this button on your calculator, but you may have a button that says 1 over x. These two buttons perform the same function. They simply flip your value so that it's 1 over that number, okay? So as you get ready to do your calculations, you're going to take your 1 over 5 plus 1 over 3, you're going to get an answer, your 0.1234, and then you are simply going to take the inverse of that answer. If you just hit the x to the negative 1 button, it'll automatically bring whatever your last answer was down and just invert it. Looking at the formula over here on the right, this is for calculating the magnification. So this is going to tell me how the size of my image relates to the actual object, and it's also going to give me the orientation. Is my object inverted or is my object upright? So the way that we're going to interpret the information here is to simply first off recognize that these are ratios. So if I'm going by the heights, I'm going to measure the height of my object, I'm going to measure the height of my image, I'm going to need those to be in the same unit so that we can get a proper relationship here. And when I do that, my units are going to cancel out, because whether I'm using my height divided by my height or my distance divided by my distance, these are going to be in the same unit. So my units will cancel. So there's no unit for our magnification. It is simply a ratio of how those distances or how those heights compare. So what are we going to interpret if we get a decimal value? Well, if I end up with a decimal value, that must mean that my numerator was a larger value than my denominator, which means that my image is smaller than the original object. So some decimal number for my m value is going to tell me that my image is reduced. It is smaller than the real life object. If I get some number 1, or not 1 means it's the same. If I get some number larger than 1, that means that my numerator must have been the larger value. So that tells me that my distance to the image was greater than the distance to the object, or the height of my image was greater than the height of my object. So this tells me that my image is larger. Okay, so that's how we're going to interpret reduced, which could also be called smaller, and enlarged, which tells me that my object is larger. My image is larger than the object. We also can interpret whether the object is upright or inverted. If my object is upright, that means right side up. So if it's a person in real life, then the image of my person is also going to be right side up. Or is my object inverted? That means my object is going to be upside down. So if in real life my person is standing right side up, but in the image my person is on their head, then that would be inverted, okay? The way that we're going to interpret this is by the positive or negative sign. If I get a positive value for my m, that means that my object is upright. If I get a negative value for my m, that means that my object is inverted. So these are the two different types of information that we can interpret from our m value. Now, in order to get the upright inverted, we need to be using the DIDO and not those height values. Here is the slide that we looked at earlier, and I said we were going to ignore the items in the boxes on the right until later. Well, it's later, so let's go ahead and take time to look at those. Remember that you are supposed to understand what happens to the light because of the curvature of the mirror. So what we're telling you here is when your mirror causes the light to converge, so the light is going to bend off the various locations of that mirror so that it causes the light to come together in a physical location, then we are going to call that converging light. We're going to call that converging light. And so converging light rays are going to be positive values for our focus whenever we go to plug that into the 1/f equation. If we have a mirror that causes the light to spread out or diverge, then we're going to have to put a negative in front of our focal length before we do our calculation. If we are using this equation to solve for the distance from the mirror to the image, when we plug in our numbers and do our algebra to solve for DI, if we calculate a positive value for my distance image, that means this is a real image. If we calculate a negative value for my DI, that means that the light did not physically meet up somewhere, and so this is a virtual image. Again, when we learn how to do the diagrams in the next lesson, I will revisit what these values mean and where they came from. and it will hopefully clear up any gaps in understanding you may have. Once again, in the bottom box, it tells us a positive M value means that my image is upright, and negative M value means that my image is inverted. So this slide and the slide with our equations are going to be the two that you're going to want to have handy as you work your practice problems for the assignment that goes with the mirrors. In the next lesson, we will learn how to do ray diagrams, and we will come back and revisit